Okay. Hi everyone. Thank you all for being here. Today I'm very happy to introduce you to Scott Melville from Queen Mary University of London. So first, let me tell you a little bit about Scott's academic background. So he obtained his master's degree at Oxford University. He then earned his PhD at Imperial College, London. He also held a postdoc position at Cambridge University. And currently, he's a Stephen Hawking Research Fellow at Queen Mary University of London. Today, his seminar title is Cosmological Scattering. So thank you very much, Scott, for accepting our invitation, and please take it away whenever you're ready.
All right. Thank you so much for having me. It's a real pleasure to see you all virtually on Zoom. So as you mentioned, my talk today is going to be about cosmological scattering. And really what I want to do is find a way to describe quantum mechanical interactions on a cosmological space-time background. And my motivation for doing this has always been to better understand the fundamental high energy physics that describes our universe. So historically, this high energy frontier has really been set by terrestrial collider experiments. Okay, you've seen pictures like this before. You make two particles, accelerate them to very large center of mass energies, and they collide and interact. And through these interactions, they decay into jets of stuff that we catch with our detectors, and we use that information to reconstruct these fundamental interactions that the high energy particles experienced. Now, that paradigm has been super successful, right? It probes energies up to 10 TeV at the current LHC, and it's how we've developed the standard model of particle physics. But of course, there's a limitation with a terrestrial collider, which is that you are always doing these scattering experiments in the very low gravitational field of the Earth, very low, weak space-time curvatures. So the talk today is going to be about thinking about the cosmological collider, a new kind of high energy frontier. The idea is to use the very early universe, to use inflation like a collider. The rapid space-time expansion is now the thing that is going to produce and accelerate heavy particles. And these heavy particles are then going to interact and decay into curvature perturbations. And it's ultimately these correlated curvature perturbations that get imprinted in the CMB as correlations that we can measure in the sky today. Now, the precise energy scale at which all of this is happening is not something that we've pinned down yet, but it really could be as high as 10 to the 13 TeV. But the important thing is that this is some quantum mechanics, some fundamental physical interactions that are happening in regions of very high space-time curvature, very strong gravitational fields. So it's an opportunity to probe a completely new regime to understand how gravity and quantum field theory should interact and be put together. So the talk today is really all about how can we take all of the machinery, all of the technology that's been developed in particle physics, and use that to better understand what's happening in this cosmological collider in this early inflationary universe. So for particle physicists, the key player is the scattering amplitude. It's a complex number whose mod square tells you about the probability that two particles come in with some known momentum, interact, and leave with some known momentum. What we measure in practice is something called a cross-section. It's basically this probability, and then you integrate over all of the allowed phase space, all of the allowed momenta with which the particles can come out. So the dream would be to write down a complex number, something like a scattering amplitude, which characterizes how correlated fluctuations are being produced in the early universe from the rapid space-time expansion. And the mod square of this complex number should characterize how likely this process is to happen and therefore be related, maybe up to some phase space integral, to the correlations that we measure today in the CMB. Okay, that's the dream. We would like a way of setting up this whole cosmological collider problem in a language which looks similar enough to the particle physics problem that we can take decades of progress in particle physics and import that almost immediately to a cosmological setting. All right, so why is that the dream? Why would I like to, match up these two pictures? Well, amplitudes are very useful for a number of reasons, but let me give you kind of the three top ones that are going to be relevant for this talk. The first reason that amplitudes are conceptually very useful is that if you're given, say, a Lagrangian, give you some Lagrangian, let's imagine I do something completely trivial to it, right? I take all of the fields that appear in my quantum mechanical path integral and I redefine those fields. I change those fields in some way. Well, you know that if you have an integral and you redefine all of your integration variables, that shouldn't change anything about the integral, right? These fields are just dummy variables, if you like. And so if I redefine all of these dummy variables, I'll land on some new Lagrangian, which should describe exactly the same physics. Then I can do something else trivial. I could do some gauge transformation. And you know that a gauge symmetry is just some redundancy of description. So this should land me on another Lagrangian, which might superficially look very different, but again, it's describing the same underlying physics. And then I can even go further. I can integrate by parts at the level of the Lagrangian. This is like adding a total derivative. This is something which is a boundary term. It doesn't affect any bulk observable. So I have this way of generating from my original Lagrangian a whole family of different, superficially very different looking field theories, but which all describe exactly the same underlying physics. And so one of the amazing things that a scattering amplitude does for you is it cuts through all of this redundancy. So all of these different theories, if they describe the same physics, they will have the same scattering amplitudes. So something like that is really what we need in cosmology, particularly for early universe cosmology, because for years we've been industriously writing down models of inflation. It would be great if there was a way of very efficiently organizing these theories and deciding which ones are genuinely physically distinct and which models of inflation just look superficially different, but are maybe just written in different variables or differ by some gauge transformation. Okay, so the scattering amplitude should do that for you. Now, the second reason why I would really like an amplitude for cosmology is that we've learned from particle physics that often these amplitudes are much easier to compute than the observable cross-section. Now, one reason that they're easier to compute is that we have many powerful techniques in perturbation theory which work wonders for computing this complex amplitude A. And roughly speaking, they come in two flavors. These techniques are either referred to as on-shell. That means that all of the particles in the scattering process have physical, real values of energy and momentum, such that p squared is equal to their mass, m squared. And on-shell techniques include things coming from unitarity, the optical theorem. Roughly speaking, these are all techniques which take complicated Feynman diagrams and give you a way of cutting them into simpler Feynman diagrams. This also includes things like the double copy, where you take two copies of, say, Yang-Mills, a gauge theory of gluons, and you stick them together and you make a higher spin theory like gravity, like general relativity. And it also includes fancier things like spinor helicity variables, the Park-Taylor formula, and so on. This is an incomplete list. But I want to contrast that with another flavor of technique, which would be called off-shell, where these particles are labeled not necessarily by real values of the momenta, but rather by complex values of p squared. So this is some mathematical trick where you allow the energies of the particles to be just free complex variables, and then you can study the scattering amplitude as a function in the complex plane. Right? Because then mathematicians know lots about how to characterize functions in the complex plane. And so you can write down useful spectral representations. So this is a way of kind of doing the opposite of the unitarity cuts. This is a way of taking simple Feynman diagrams and then gluing them together to make more complicated Feynman diagrams. It also includes things like crossing symmetry, so you can relate different physical processes to each other, and then more complicated things like BCFW, which might come up again at the very end of the talk. But really today, I want to highlight that there's just a long list of powerful techniques that give you ways of doing difficult perturbative computations. And the upshot of all of these techniques is that in particle physics, in theories on a fixed Minkowski space-time background, we've been able to compute these scattering amplitudes to very high orders in perturbation theory. So in simple theories like the most supersymmetric gauge theory you could have, n equals 4 super Yang-Mills, we know amplitudes with up to 6 external gluons and with up to 8 loops. So this is like next to 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 leading order in perturbation theory. If you want to come closer to reality and give up supersymmetry, in QCD, people know amplitudes at lower multiplicity, but still up to something like 4 loops, which is next to next to next leading order in perturbation theory. And then more recently, we've seen an explosion of interest in computing these scattering amplitudes in general relativity, because these scattering amplitudes can be related to the gravitational waveforms that we measure at observatories like LIGO and Virgo and CAGRA. So there, I think the state of the art at the moment is what's called fourth post-Minkowski order in that vernacular. It really means computing a scattering amplitude with up to 3 loops. Okay. So what I find really, really amazing is that when you turn to something like the cosmological collider, where now the background space-time is not asymptotically flat, but is rapidly expanding. I mean, I'm still trying to wrap my head around this diagram. This is a tree-level Feynman diagram where you just have 2 interaction vertices and 4 external legs. This diagram is very important for working out the 3 and the 4 point correlation function you would expect to see in the CMB. And in many ways, it is the frontier of what we can do perturbatively on an expanding space-time background. If you have a generic mass for the particle on this internal line, I mean, kind of the nicest representation we have of this diagram is from a paper from late 2018, which expresses it as an infinite sum of hypergeometric type functions. And probably there's a way to write it in a simpler form, but this is really just to emphasize that the frontier of what we were able to do on a rapidly expanding space-time background is kind of a few decades behind what we've been able to do on an asymptotically flat space-time. And that's exciting because it shows that there's so much potential. The fact that we have these powerful techniques that can go to such high loop orders and get very, very precise results for things like the LHC and for gravitational wave observatories, I think that really shows what's possible. It shows that we should be trying to do the same thing for inflation. We really ought to be able to compute equally precise observables and make equally precise predictions for correlation functions in the CMB. Now, the final important thing about scattering amplitudes is that they're really an important discovery channel. It's a way that we can learn about what are the new states, the new fundamental physics that is dictating how these particles are interacting with each other. Okay. So there's a cartoon of this, which I'm quite fond of, which is that if you imagine at very high energies on very small spatial scales, there's some detailed high energy model that describes your universe, it will have some corresponding high energy scattering amplitude, which depends on kinematic variables like the center of mass energy and the momentum transfer. These are so-called Mandelstam variables, S and T. Now, in practice, this is not what you measure. In practice, what you measure is some very low energy scattering process. It's a bit like you're measuring the Taylor series coefficients of this amplitude. So you can ask a very concrete question, which is, if I can measure the first few Taylor series coefficients of a function, what can I learn about the underlying function? So this is a project which goes under the name positivity bounds, and there was again a recent SNOMAS review that contains all of the relevant citations. The kind of poster child result here is that suppose you measure one of the lowest Taylor series coefficients, it must be a positive number if this underlying high energy physics satisfies some basic requirements like it's causal and local and unitary. So that's exciting because it means that if you do a low energy collider experiment, you scatter pions, for instance, and you measure this coefficient and you find that it's negative, you immediately learn that whatever's happening on small scales violates one of these fundamental assumptions that we almost always make, that we just take for granted. Now, you might be quite surprised if pion scattering kind of secretly violated causality somehow, but you might be less surprised if something in the very early universe, where we think quantum gravity effects might be important, if you wanted to diagnose whether quantum gravity actually satisfies our kind of classical notions of causality and locality, this would be a way that you could actually check. Okay, now there's one final point that I want to make here, and it's a little bit more technical, but I think it's really interesting. So bear with me for just a minute, and I'm going to try and explain how understanding these scattering amplitudes as analytic functions of complex momenta, how it gives us a way of seeing new particles, new physics that we would be completely blind to otherwise. So the prototypical picture that we often see, right, is something like this. This was the discovery of the Higgs boson by the Atlas detector at CERN. You measure the cross-section at lots of different energies, and you find that there's a bump. You find that there's a special energy at about 125 GeV, where suddenly the cross-section increases. Now, this value, 125 GeV, is then what we interpret as the mass of the Higgs boson. And the reason that there's a bump, or one way to think about this bump, is that we're measuring physical cross-section as a function of real center of mass energies. But if you play this trick of extending this observable into the complex plane, this function in the complex plane actually has a singularity. It has a pole at a particular value of complex center of mass energy. And it's that singularity which we interpret as a new field, a new degree of freedom, the Higgs boson. And the fact that the singularity is close to the real axis is why we see this bump. Good. So that's the cartoon that most kind of particle people have in mind when they do collider experiments, right? They look, here's a different set of data, this time from pion scattering. What they're looking for are sharp features. They're looking for kinks, bumps, things that look like singularities. Because, for instance, in this pion data, you see things look nice and smooth until about 1000 MeV, where there's a sharp corner. And sure enough, if you take this function and you imagine extending it into the complex plane, you'll find that that kink corresponds to there being a pole, being a singularity around 1000 MeV, which, you know, is roughly the mass of the rho meson. So this is how people went about discovering new kind of bound states of quarks back in the day. Now, the reason I'm describing these cartoons is that something which is a more modern development is that looking at this picture, your eye is immediately drawn to what's happening around this kink, and you might not be at all suspicious about what's happening around 500 MeV. That looks like it's perfectly benign. It's basically a straight line. But what you learn by playing this game of going into the complex plane is that if you extend far enough into the complex plane, you will find that there has to be another singularity. There has to be another pole very far from the real axis. And experimentally, it's determined to have an imaginary part, which is more than half its real part. So it's kind of very far from the real axis. And it's now identified with a different kind of meson. It's a different kind of physical bound state between two quarks. And it's something which you would have never guessed just looking at these kind of real energies. It's only something that becomes manifest when you play this game of going into the complex plane. But it's a real state that exists in our universe that you might have otherwise missed. So what I'm going to do for the rest of the talk is kind of explain how we can build something like a scattering amplitude for cosmology. And this is kind of going to be the the grand application at the end. So at the end of the talk, I'm going to come back to this and I'm going to show you that if we are measuring correlators in the CMB, there are some very characteristic patterns which we often associate with new states during inflation. That's kind of like this bump. But actually, what's really interesting is that even if the CMB looks perfectly flat, right, there doesn't seem to be any oscillatory patterns, if you're able to extend into the complex plane in this careful way, you can still infer the existence of new states. It could just be that there are poles, there are singularities very far from the real axis. And that's why you don't see the bump, but you can nonetheless infer that they're there. Fantastic. So are there any questions about that? That's the kind of grand big picture motivation. What I'm going to do now is kind of go pedagogically through how we build something like an amplitude and then what we can use it for in inflation.
We're good.
No, we're good. Okay, brilliant. So what I'm going to do now is, before diving into quantum field theory on a de Sitter spacetime background, I want to give a much simpler example, which is just a toy model of solving scattering in one-dimensional quantum mechanics. And actually, it turns out that this 1D quantum mechanics is enough to see a lot of the relevant features, a lot of the relevant conceptual issues that are going to come up when we try and do this on a de Sitter or on an expanding spacetime background. So the toy model I have in mind is the Schrödinger equation. We want to solve for this wave function, psi. It depends on spatial position x. And you've got some potential v of x, which appears in this equation. Now, of course, if you turn the potential off, if there's no potential whatsoever, then the Schrödinger equation is easy to solve. You can write a general solution as a linear combination of waves that travel to the right and waves that travel to the left. Now, what's often more interesting is when you have a potential which is non-zero in some localized region of space. So what that means is your potential goes to zero at large and small x. And so you can, for instance, when you're far away from these perturbations, send in free energy eigenstates. You can send in, say, a right-moving plane wave. And what will happen is this right-moving plane wave will hit the perturbations, and some amount of it will be transmitted with some complex coefficient t, and some amount will be reflected with some complex coefficient r. You can, of course, do the same thing from the right-hand side. You can scatter left-going plane waves, and some will be transmitted and some will be reflected. And so a complete characterization of this potential are these four complex numbers, the reflection and transmission coefficients from scattering from the left and from the right. And so it's conventional to organize these four complex numbers into a 2x2 matrix. So this is the S matrix. And the reason that you do this, practically speaking, is that if you think about a collider, this is kind of the experiment that you're going to do. There's some, kind of bulk interaction region deep inside your collider. You don't really have access to that. All you can do is throw in plane waves, either from very far away on one side or from very far away on the other side, and measure what comes out. So this thing is really a kind of pragmatically useful way of characterizing what is going on kind of in the bulk of your interaction region. Now, why a 2x2 matrix, you might ask? Well, one reason that a 2x2 matrix is useful is that when you turn the interactions off, so if you turn the potential fluctuations off, this 2x2 matrix just becomes the identity, right? It corresponds to the transmission coefficients being 1 because the plane waves then just happily propagate without scattering off of anything. So it's conventional to take this S matrix and split it into a non-interacting identity piece plus some shift that contains all of the information about delta V. So this is the amplitude that I introduced on the very first slide. If you like, it's the interacting part of the S matrix. So that's one useful property that this 2x2 matrix has. Another useful property is that it's a unitary matrix. The reason that it has to be a unitary matrix is if you think about what's happening to the total probability, if you add up the probability that you get reflected plus the probability you get transmitted, that has to be 1. And so if you take this 2 by 2 matrix and work out, what its product with its own conjugate is, you find that it therefore has to be the identity matrix. Now, why that's important is if you then write this in terms of the scattering amplitude A, what you find is that A, therefore, has an imaginary part, which is related to its mod square, which is a positive number. So the fact that this amplitude has a positive imaginary part, that positivity is ultimately where these positivity bounds that I mentioned come from. So how do you infer that the low energy part of your scattering amplitude, say the coefficient of s squared in a low energy expansion, how do we know that that has to be positive in any kind of unitary UV completion? It ultimately comes from the fact that we know that whatever the high energy physics is, if it's conserving probability, it has to have a positive imaginary part. So this positivity kind of really plays an important role in deriving these relations between what's happening in the UV at very high energies and what's happening in the IR at very low energies. Now, there's a final property which this S matrix has, which again is very useful, which is that it's an analytic function when you take the momenta here, the k that describes the plane wave. If you imagine taking this k and making it some complex number, what you find is that this S matrix is analytic. It's an analytic function in the lower half of the complex plane. Here, analytic just means that it doesn't have any singularities. So if you draw the complex plane, you'll find that this function basically is nice and smooth, and it can only blow up at points in the upper half of the complex plane. Now, knowing something like this about your S matrix is then very important when you try and do the kind of discovery channel stuff that I mentioned at the beginning. If you want to measure this S matrix on the real axis and then try and extend it into the complex plane, this is telling you where you might expect to find singularities. Now, the fact that it's an analytic function in the lower half of the complex plane, that actually has a real physical underpinning. It comes from causality. So this is not something which I'm going to fully elaborate in this talk, because it would take most of the talk. The idea is that you can solve this equation for the wave function in terms of some propagator, some Green's function. And just like for scattering on Minkowski, for those that are familiar, there's something like a Feynman propagator, p squared minus k squared. And then there's some I epsilons here that tell you about the time ordering, that tell you about the causal relations between your fields at different space-time points. And so it's really that kind of I epsilon prescription, which then translates into some statement about the analytic structure of the wave function, and therefore the reflection and transmission coefficients that you would expect to find. But the main takeaway here is that the third useful property of this object is that it's an analytic function in at least half of the complex K plane. And so those kind of three features, the fact that you can separate the S matrix into a trivial non-interacting piece plus an interesting amplitude, the fact that this amplitude has a positive imaginary part, and the fact that this amplitude is an analytic function in at least half of the complex plane, those are really the foundational properties on which all of these perturbative techniques that I mentioned, they all rely on those kind of basic properties. Good. So now I want to turn my attention to what happens in cosmology. So why is it hard to take these techniques, to take these principles and apply them in cosmology? I mean, roughly speaking, the problem is just that the space-time background is no longer flat, so you've lost some symmetry. You no longer have Lorentz invariance, and that complicates a lot of the calculations. This quantum mechanics example is nice because it lets us see exactly what kind of thing can go wrong. Suppose I have a potential which does not vanish asymptotically. So this is a potential which is no longer asymptotically flat. It's no longer going to zero at large and small x. It's a potential, I've just picked one that goes like 1 over x squared. Now, a potential like this, at very large x, it's very close to being zero. So you have the usual left and right moving plane waves that we just saw. But very close to the origin, this potential becomes very important, right? It actually dominates this Schrodinger equation. It's much more important than the energy term. And what you find is that these plane waves, they transmute. Instead of being left and right moving exponentials, they become left and right moving power law solutions. Okay? So the character of your solutions changes dramatically. Now, what this means for scattering, constructing some kind of scattering experiment, is suppose you have this potential plus some small wiggles, some small perturbation in the middle. You could imagine doing the same scattering problem. You send in a right-moving power law solution from the origin, and now there's some probability it gets transmitted, and there's some probability it gets reflected. You could do the same thing from large X. You could send in a left-moving plane wave, and there's some probability it gets transmitted as a power law, and some probability it gets reflected as a plane wave. And this gives you a complete characterization of the potential. Now I've added twiddles, I've added squiggles above everything to just remind us that now we're talking about a slightly different problem, which is scattering on top of a background which is non-trivial. So this seems like the natural generalization, right? This is kind of naturally what you would do if you open a quantum mechanics textbook and you just try and follow all the same steps, but on a kind of cosmological space-time background. But immediately you run into some important differences. Right? The first important difference is that even if you turn off the wiggles, if you turn off the perturbations, this matrix does not become the identity. It does not become the identity because these plane waves that you're, say, sending in from large X, they can essentially scatter off of the background. A plane wave will not stay a plane wave all the way to the origin. It will transmute into something else. Now, in the cosmological context, this is what we call particle production. And here we're seeing exactly the same effect, but in a very simple kind of 1D quantum mechanics setting. It's really just saying that because you have some, even the free background potential, because it's non-trivial, there's some non-zero probability that if you start sending in, say, a plane wave from large X, you can solve the Schrodinger equation in this case exactly. The solution is something like a Hankel function. And for those that know about the asymptotic behavior of Hankel functions, if you expand a Hankel function at small x, you find that it isn't definitely left or right moving. It's some linear combination of the two. Very good. So that's the first kind of important difference, that you no longer have this clean split of this S matrix into a trivial non-interacting piece plus an interaction piece. Even in the free theory with no wiggles, because the background's non-trivial, you have some non-zero probability that you kind of go from what is basically a left-moving particle into some combination of left and right-moving particles. Now, this has kind of knock-on effects when it comes to looking at things like unitarity, because it's very hard to separate the amplitude, the interacting part, from the non-interacting part. It's not clear whether there is any object with a positive imaginary part. And also, if you compute the analytic structure of an object like this, it will not be analytic in half of the complex plane. Typically, an amplitude like this has singularities everywhere. It can have singularities in the upper and the lower half of the complex plane. So it's kind of missing a lot of the foundational properties that we rely on so heavily in particle physics. But fortunately, this is a problem that you can fix. Now, the way that you would fix this problem is you would kind of take this cartoon at the bottom and you would use it as motivation to change your asymptotic scattering states, right? No one says that you have to use left and right moving eigenstates near the origin. You could instead ask a slightly different question, which is, if I send in a plane wave, what are the chances that I will transmit this particular linear combination of left and right moving power laws? Okay? Because this particular combination is the thing that would appear in a free theory. These are free energy eigenstates. So this gives you an alternative description, an alternative characterization of this S matrix. which is now a new set of 4 complex numbers, which describe the transmission and reflection of plane waves and these free energy eigenstates from this potential. So this kind of sleight of hand, it seems like just some mathematical trick, but really what it's doing is it's restoring all of those properties that we need this S matrix to have. So in particular, this S, now, if you use these right asymptotic states, it has the feature that when you turn off the interactions, then by construction, it becomes the identity matrix. So now there's a very clean split into, nothing interesting happens, plus some interactions happen. Unitarity then immediately tells you that the imaginary part of the scattering amplitude is a positive number. And it turns out that this function, again, by causality arguments, is an analytic function of complex momenta in the lower half of the complex plane. So this is really the thing which is a much more natural analog of the scattering that we do in particle physics.
Scott, sorry?
Yes, go ahead.
I know this is talking about, but these F eigenstates are eigenstates of what exactly? Just a Hamiltonian or something?
Yes, very good. They're eigenstates of the Hamiltonian. And okay, that's a good question. So this will come up when we talk about the de Sitter problem. Here, what you're using near the origin is this combination of left and right moving plane waves. So they're not eigenstates of left or right motion, but what they're eigenstates of are what right and left moving, what left and right motion look like if you translate them using the free theory translation operator from large x to small x. So in the context of cosmology, right, we're about to take this picture and basically wick rotate the whole thing so that now instead of talking about motion along the x-axis, we talk about particles moving forwards in time. And the distinction in cosmology is going to be whether you talk about particle eigenstates at late times, so that's states at late times that look like, definitely one particle going in or definitely one particle going out, or whether you talk about a linear combination of particle and antiparticle, which if you like is just the kind of free theory evolution of what a particle was in the far past. If you evolve a particle from the far past to the far future, because of particle production, in the far future, you won't land on a single particle anymore. You'll land on some linear combination of particles and antiparticles.
Okay, but the label will be the energy of the particle, so to speak, or what?
Yes, that's right. Yeah, they're labeled by the energy that they had when they were sent in at early times.
Okay, perfect.
Yeah, that's right. Yeah, perfect. Okay, fantastic. Great. Yeah, good. So this is summing up the toy model. So that's everything that I want to tell you about one-dimensional quantum mechanics. Because now we're going to proceed essentially by analogy. So in one-dimensional quantum mechanics, the thing you should take away is that when you have a potential that doesn't vanish at the boundaries of your scattering region, then you are forced to make a choice. You can either scatter what are left or right moving eigenstates, and that gives you an S matrix, but it's an S matrix that describes scattering from both the background and scattering from the perturbations. And because it's mixing the effects of the background and the effects of the perturbations, there isn't a clean split into a scattering amplitude and a non-interacting piece. And so things like unitarity and analyticity are harder to implement. You could instead scatter free energy eigenstates, which gives you an alternative definition. It's ultimately some Bogoliubov transformation. It's the S matrix written with respect to a different basis, but it's a basis that's adapted much better to describing just scattering from the perturbations, and therefore implementing things like unitarity and causality is much simpler. Okay, good. So with that long introduction, now I want to describe some work I did with Guy Pimentel. This was kind of last autumn, where we wanted to define an S matrix, a scattering amplitude, for a de Sitter expanding spacetime. Okay. So now we're going to change gears, and instead of one-dimensional quantum mechanics, we're going to talk about quantum field theory on a d-dimensional de Sitter spacetime background. So the coordinates we're going to use are so-called conformal time tau. This is like the expanding Poincare patch. Really, these coordinates describe when tau goes to minus infinity. This is kind of very early in the universe's history before inflation starts. And when tau goes to 0, that corresponds to the very end of inflation. And what we would like to do is put on this expanding space-time background a scalar field. So this scalar field is basically a proxy for the scalar curvature perturbations that you create in the metric and then which go on to seed correlations in the CMB and in large-scale structure. And we'll write the scalar field equation of motion in a very suggestive way. There's a linear part plus some interactions, and all the interactions I'll just absorb into some current J of phi. So this J is very much like the potential V of x that we had in the 1D quantum mechanics example before. So we can start by solving the problem when J is 0. So suppose there's no interactions, you just have a perfectly free scalar field. This is a problem that we can solve exactly. It's just a linear equation of motion. And what we find, if you quantize this free theory, at very early times, a particle is described by a plane wave, something like e to the ik times the conformal time. And an antiparticle, a particle moving backwards in time, would be e to the minus ik tau. But if I look at late times towards the end of inflation, the particle and the antiparticle eigenstates, they're now described by these power law solutions. It's again a complex conjugate pair, but you notice that you've transmuted from plane waves to now these things that look like power laws. Okay, good. Now, here's a box with some kind of technical clarification about what I mean by this cartoon. So this cartoon is saying that, oh, a particle at late times somehow looks like a power law. What does that mean? What that means is to canonically quantize the scalar field, right? You want to promote it to being an operator. And so the canonical way to do this is to find a solution, a so-called mode function, f, a solution to the equations of motion, which is then going to carry the time dependence of your scalar field. And then what's left, you call an operator a hat. And then because the scalar field is real, you need to add the complex conjugate, right? Some conjugate operator a dagger. Now, you're free to choose any mode function you like. F just needs to solve the equations of motion, but if I give different boundary conditions for F, if I choose different solutions to the equations of motion, then this will define for me different A and A dagger. It will define different annihilation and creation operators. So the idea is that if you choose these plane wave boundary conditions in the far past, so if you use mode functions that scale like plane waves in the far past, this defines for you an operator A, which annihilates the vacuum, annihilates the ground state of the system in the far past. But if you instead chose a different boundary condition, these power law boundary conditions for the mode functions at late times, it defines a different annihilation operator, which annihilates a different ground state that would be annihilating the ground state at late times towards the end of inflation. Good. Now, if A is an annihilation operator, which is annihilating the ground state, then just like in Minkowski QFT, what you can do is think of A dagger like a creation operator, which is creating particles, creating excitations on top of the ground state. So the notation that we use for this is if you take the vacuum at very early times and you hit it with n creation operators, what you're creating is a state n comma minus infinity. So n tells you how many particles are in the state, and minus infinity tells you the time at which there is this many particles. Now that's important because what we'll see in a moment is, suppose you start with 2 particles and you let the system go, you're not going to stay with 2 particles for very long. Because the space-time is expanding, you can create pairs of particles from the vacuum. If you start with 2 particles at minus infinity, at late times, you're going to have some superposition of lots of different particles, a whole sea of kind of Gaussian noise. Okay, so the fact that you have these different boundary behaviors for your equations of motion means that you have these 2 different states, these 2 different n particle states that you can define. A state that has exactly n particles in the far past and a state that has exactly n particles in the far future. Very good. So the natural S matrix that you might want to define, and a lot of the literature that came before us, I think implicitly had this definition in mind, is you would want to define something like the following overlap. You would like a complex number which describes the probability that you start with n particles at early times, that's the state that goes into your system, and then at late times you end up with exactly n prime particles. So the cartoon, say for 2 to 2 scattering, it would be something like this. You send in what are basically plane wave solutions, and you're asking about the transmission and reflection coefficients into something that looks like a power law decay. So this is an object we called the Unruh de Wit S matrix. Unruh de Wit because if an observer had an Unruh de Wit detector, an actual particle, like a Geiger counter that clicks when it detects particles, this detector would click twice at early times, and then it would click twice at late times. So you have definite numbers of particles. But as this notation maybe suggests, the fact that I've put squiggles here is that this object, this Unruh de Wit S matrix, lacks a lot of the nice features we might hope an S matrix should have. In particular, if you turn off the interactions, it does not just become the identity. And it doesn't become the identity precisely because of this particle production effect. It also means that, for instance, the analytic structure of this object is much more complicated. So here's a cartoon to kind of show what's going on. If you start with a state that has 2 particles in the far past and with no interactions, then these 2 particles will just fly past each other and come out at the end of inflation. But that's not all that will come out, because you can also create correlated pairs of fluctuations just out of nothing, out of the vacuum. You will generically create not just the 2 ingoing particles, but also this correlated Gaussian sea of pairs of fluctuations. And it's for exactly the same reason that we saw in 1D quantum mechanics. In the free theory, I can solve this equation exactly. Again, it's some Hankel function. And I find that an ingoing plane wave actually just becomes this kind of linear combination of particle and antiparticle. Good, very good. And one kind of knock-on effect that has, if you try and compute these objects, actually the first thing that we tried to do is just roll up our sleeves and compute these things. You find that even simple S matrix elements have complicated analytic structure, that they have poles in both the upper and lower half of the complex plane.
Scott, sorry. I think we have
Yeah.
Can I think of that as a Bogoliubov transformation? This Unruh de Wit S matrix that you say, relating some vacuum state to some other vacuum state at different time?
Yes, fantastic. Absolutely. So this is very much a Bogoliubov transformation. And if you like, this is the mode function of some kind of alpha vacuum, basically. What this is saying is that this out state that you're trying to use, the state that has exactly n particles, that's got nothing to do with the Bunch-Davies vacuum, right? The vacuum at late times, that's not the kind of standard Bunch-Davies vacuum. That's some other state which has mode functions that are kind of power law decays. So you're absolutely right. And in fact, that's the way to solve this problem. So just like in the quantum mechanics analogy, you have this object which you can define and write down, but it lacks some of the nice features you might want it to have. And so instead, you can perform essentially the inverse Bogoliubov transformation. What you can do is, instead of using these out states, which correspond to having a definite number of particles at late times, you can use a different set of out states, which really correspond morally to the top half of this cartoon. So suppose in the free theory, you send in two particles, and then at late times, you measure 2 particles plus the sea of noise. Well, what you can do is use this kind of asymptotic behavior to define an out state. And you can ask, what is the probability that if you send in 2 particles, what's the probability that you will transmit those 2 particles plus the free theory kind of particle production stuff, right? Now, that's a much more natural question from the point of view of inflation, because we think that the interactions during inflation are very weak. So if the interactions during inflation are very small, then this S matrix you would expect to be very close to the identity. Because this S matrix is really just asking, what are the chances if you send in two particles that you find the free theory answer at late times? Good. Now we give this a name. We call this the Bunch-Davies S matrix, exactly because of what you mentioned, that this out state that we're using now, it's really defined with respect to the vacuum at minus infinity. So now both the in and the out state know about the Bunch-Davies vacuum. And you don't have to introduce any kind of alpha vacuum or any kind of other state. And so this has, yeah, go ahead.
What's the difference of that between the in scattering elements, say?
What's the difference between an in?
Yes, because these are asymptotic states at minus infinity, right? So I don't understand the nomenclature of out and in.
Yeah, fantastic. So out means that this state in the interacting theory coincides with the indicated state at late times. And in means that it's the theory that coincides with the designated state at early times.
Okay, so you're just using the basis of the Bunch-Davies vector as a basis for the out state as well.
Yeah, that's right. So this cartoon is exactly to try and to tease apart the difference between what does it mean to have minus infinity in and minus infinity out. So what this notation means is what you should do is first look at the ket, and it tells you what free theory state you're kind of starting from. And the free theory state kind of gives you possible boundary conditions that you can use in the interacting theory. Because the idea is that in the interacting theory, the interactions only take place in the bulk. Like at very early and very late times, the interactions turn off because the particles get very far away from each other, so they no longer feel each other. So the free theory state kind of gives you natural boundary conditions that you can use in the interacting problem. And so the in and the out subscripts are basically telling you whether to impose this boundary condition at early or late times. So that's what the in and the out means. It's kind of telling you when you should impose this free theory boundary condition. Does that help?
Yeah, all right, yeah.
Okay, brilliant, very good. So this is in the Heisenberg picture. You could also write this in the Schrodinger picture where the states evolve in time. And then what this would really be is like starting in a state that has n particles. And then there would be some time evolution operator u, which evolves it to late times. And then at late times, you project it onto some Bunch-Davies state. Yeah. Now you asked what is the difference with like an in-in correlator. So an in-in correlator, that in the Schrodinger picture would be like having not just one time evolution operator u, but having something like u dagger. It would be like something like you evolve to the far future, and then you insert some operators, and then you evolve back to the far past, and then you project onto the Bunch-Davies vacuum in the far past. So that's the difference between in out and in this language. Okay, good. Fantastic. So I'm coming towards the end of the hour. So what I want to do is close with some of the properties that this S matrix has. So one kind of very useful, well, one natural question you would have is, how is this related to observation? So how is this related to the correlation functions that I measure in the CMB? So for instance, if you want to know how correlated are, say, a measurement of 3 fluctuations in the CMB, one way to characterize that correlation function is to imagine integrating over all possible field profiles that inflation could end with, weighted by the probability, so the mod square of some wave function, so the probability that inflation ended in that state. Right? Now, this probability, the wave function at the end of inflation, okay, this is one way to parameterize it as the exponential of a sum of so-called wave function coefficients. And the reason we parameterize it this way is that, again, if the interactions during inflation are small, then this wave function is very close to being Gaussian. So small interactions means that these wave function coefficients, there's a Gaussian width, which is much bigger than the Gaussian, than the skewness of the distribution, which is much bigger than the kurtosis, and so on. So there's a natural perturbative ordering of these different wave function coefficients. Okay. So conventionally, we would say that if you can compute say these wave functions, if you compute the wave function coefficients, then you can do this integral and you can compute the correlation that you would expect in the CMB. Okay, so turns out that these wave function coefficients are related to the S matrix elements that I just defined in a very simple way. There's a simple linear relation between the two. And the reason that there's a simple linear relation is that this wave function, this probability that you end inflation in a given field eigenstate, if you think about it in kind of quantum mechanics language, what it's asking is, if I start in the Bunch-Davies vacuum, if I start in the vacuum at very early times, if that's my in state, and I project it at late times onto a field eigenstate, that complex number, when I mod square it, is the probability that I need. But since my J particle eigenstates, they're a complete basis. So I should be able to take any state in my Hilbert space, including a field eigenstate, and expand it as a sum over these n particle states. So the fact that there is such a relation, a linear relation between field eigenstates and particle eigenstates, means that there's a linear relation between these wave function coefficients and these S matrix elements. And so if you, yeah, good. So the crucial thing here is that these coefficients, they're known. These are model independent kind of kinematic factors that don't care about the interactions that you have. All of the dynamical information about the interactions are encoded in these S matrix elements. Now here I gave an example actually of the inverse relation, which says like what is an S matrix in terms of these wave function coefficients. And what this example is supposed to highlight is that one kind of annoying feature of the wave function coefficients is that these wave function coefficients are not invariant when you do things like field redefinitions or gauge transformations. If you redefine your fields, you're kind of changing the basis that you're using to define your wave function. So if you redefine your scalar field, you will shuffle all of these wave function coefficients around. Okay, but what happens, and this is kind of something of a miracle, if you look at these relations, right, that construct S matrix elements from wave function coefficients, it turns out these are exactly the right combinations of wave function coefficients which remain invariant when you do something like a field redefinition. So in this example, if you do a field redefinition that changes psi4, it changes psi4 and psi6 in ways that, up to a factor of the power spectrum kind of exactly cancel in this linear combination. So although these wave function coefficients are objects that know about the field basis, when you combine them in this way, you find some kind of dynamical information, some measure of the interactions, which is independent of your field basis. Okay, very good. So what I want to do next is because I think I'm out of time. You can correct me if I'm wrong, but I have maybe like 1 minute to summarize, and then we'll call it to a close. Is that right?
Maybe you can have like 5 minutes, but no longer than that because they're going to kick out of the room. So, yeah.
Okay, fantastic. Okay, brilliant. Yeah, so it'll just take 1 or 2 minutes. So here, what I've tried to do today is kind of really emphasize why having a scattering amplitude for the early universe would be very useful, and then try to really sketch in a kind of simple 1D quantum mechanics model why that might be tricky. It might be tricky because when you have interactions that are, or if you have something non-trivial happening near the boundaries, you need to be careful with how you define asymptotic states. And so the main punchline from the paper that I wrote with Guy last autumn, the main punchline in that paper was that for quantum field theory on de Sitter, you can basically define asymptotic states carefully and write down a Bunch-Davies S matrix, which has all of the nice properties that you would want, that separates cleanly into an interacting part, which has a positive imaginary part, and which is analytic in the right half of the complex plane. So the really final thing that I wanted to do here is showcase now what would be classed as the first off-shell technique that you could now use for describing the cosmological collider. So everything I've said until now has really thought about on-shell fluctuations. So we've defined asymptotic particle states with real values of the momenta. because we have in mind that you measure correlations in the CMB that have real wave vectors. But you might ask, well, now I have this construction that looks a lot like the Minkowski amplitude. What happens if I take those objects and I analytically continue them to complex values of the momentum? So there are some technical details which I'm gonna skip, and I can always go back to them if there's time at the end. But the main plot that I kind of want to leave you with is this one here, that we often think of the cosmological collider, the idea that you can produce, say, a heavy particle with some effective mass in the early universe, which then decays into curvature perturbations. We imagine that it would show up in a correlator, something like this. If you measure, say, 4 points in the CMB as a function of the lengths of the sides of that quadrilateral, you can vary the shape of the quadrilateral, and you would expect to find these characteristic oscillations, these wiggles, where the frequency of the oscillations is set by the mass of the field that you exchanged. Now, what going off shell lets you do is it gives you a representation of this correlator, right, of this complex number S, as an integral of some kinematic, purely kinematic factors that are uniquely fixed by the de Sitter symmetries, basically, multiplied by something called a spectral density. It's multiplied by a weight that looks basically like the Bright-Wigner peak, that looks like the bump that we are familiar with from particle physics. The spectral density looks exactly like the kind of Feynman 1 over the mass squared minus some effective kinematic parameter squared. Now, what this means is you now have a concrete way of seeing these telltale kind of smoking gun features in the CMB. You have a way of seeing them as singularities, as poles in a complex plane, the plane of some effective kinematic parameter nu. Now, if the pole is close to the real axis, it means the spectral density has a bump in it. And so when you do this integral, you land on correlators that wiggle. But you could have models of inflation in which there are some new states, some new physics, a bit like the sigma meson, which are very far from the real axis. Now, these singularities, they give you smooth spectral densities on the real axis, so spectral densities that don't bump. And if you compute from them the corresponding correlator, you don't see any features, at least by eye. But what I find interesting about this is, given sufficiently precise measurements of, say, a non-Gaussianity in the CMB as a function of the momentum ratio, even if the data, has fairly large error bars or doesn't have any obvious wiggles, there is now this mechanism, this machinery for extending it to the complex plane, extending your data to complex kinematics and searching for new states, searching for new fields that were around during inflation by looking for singularities in a complex plane. So that's kind of the main thing I wanted to leave you with today. The summary is that the dream was to write down some kind of complex number which characterizes the likelihood that you would create correlated fluctuations in the early universe. This complex number, the mod square, should be related to what we measure in the CMB. And so what I've put forward today is a precise definition of such a complex number. It's an overlap in a Hilbert space of carefully constructed asymptotic states, which has the nice feature that it separates cleanly into an identity plus an interacting piece, which I should say in the flat space limit, this interaction basically becomes the Minkowski scattering amplitude that we're all familiar with. Now, the kind of technical things that I skipped were how to define Mandelstam operators, which again is kind of a useful technical trick, which lets you compute in perturbation theory any tree-level Feynman diagram. So we were able to write down, no matter how many fields you have, how they interact with each other, as long as you're talking about only tree-level diagrams, you can write any kind of Feynman diagram in the following kind of universal form. Again, parameterized by a number of these coefficients, so basically Taylor series coefficients, which we think would be a kind of natural basis that we can use when searching for these signals in CMB data. Good. Now, the scattering amplitude has the nice feature that its imaginary part is positive. That just follows from unitarity, like I described. And this spectral representation, this way of splitting this tree-level exchange diagram into an integral of two kinematic things divided by something that looks like a Feynman propagator, this gives you a really nice way of now searching for new states, new resonances, as poles in the complex plane rather than as wiggly oscillatory features in the CMB, which might be hard to detect. So I'll end there. But thank you so much again for inviting me in for all of your good questions.
Okay. And now you could hear that we were clapping. So we're very out of time. So maybe we have time for one little very fast question. Go ahead.
So, what do you mean by measuring in the pole? For example, we have CMB, we can measure correlations, right? And then we see wiggles or no wiggles. But how do you measure something in the complex plane in states and submit? I mean, practically, not on paper.
Yeah, fantastic. No, it's a good question. And actually there we're lucky because people in the collider community have sort of a long history of doing this. So the way they do this, as far as I understand it, for something like the pion example I gave, the idea is you make measurements of the pion cross-section as a function of energy. So you're talking about real scattering energies, and you basically draw this curve. You draw some best fit curve. Now this defines for you a function on the real axis. And so those are your measurements. That's where your data lives. And then your goal is to ask what happens when I analytically continue this function into the complex plane. So there's a unique way to do this. So there's a unique extension of this function into the complex plane. And you then look at that extension to see where it might have singularities. So your data is kind of giving you this extension. And then in the extension, you see that there would be poles.
Yeah, that's good. Okay.
Okay, unfortunately, we do not have any more time for questions. So let's thank again, Scott. Thank you, everyone, for coming today. Hope to see you again in the next.
Great. Thank you very much, everyone. Goodbye.
Bye.